Hello, everyone. Last week, we started fundamental topic related to concurrency and mutual exclusion and synchronization. And this week, we will continue talking about concurrency, in particular, mutual exclusion requirements and the communication levels or the cooperation levels or the awareness level between processes, followed by the hardware approaches to support mutual exclusion. So, and last week we talked about the software approaches. In today's lecture, we will talk about the hardware approaches as well as the operating system and the programming language approaches. So operating system and programming language, they do approach enforcing the mutual exclusion using different strategies and methods, including semaphores, monitors, message passing. I will also go over classical problems to cryptocurrency, which is called the producer-consumer problem. And then I will show you how this problem could be later solved using either the semaphore, the monitor, or the message passing. So as discussed last week, we can classify the ways in which processes interact with each other on the basis of the degree to which they are actually aware of each other existence. As we can see in this table, three possible degrees of awareness plus the consequences of each. The first one is processes unaware of each other. These are independent processes that are not intended to work together. The best example of this situation is the multi-programming of multiple independent processes. These can either be batch jobs or interactive sessions or even a mixture among these. Although the processes are not working together, the operating system needs to be concerned about the competition for resources. For example, two independent applications may both want to access the same disk or file or printer. At this point, the operating system must regulate these accesses. The second level of awareness is the processes are indirectly aware of each other. These are processes that are not actually aware of each other by their respective process IDs, but that share access to some object, such as input-output buffer. Such processes will exhibit cooperation in sharing the common object. The third level of awareness that we should understand it in order to enforce mutual exclusion to guarantee well synchronization between the multi-running processes or thread is processes are directly aware of each other. These processes in the third category are able to communicate with each other by process ID, and they are designed to work jointly on some activity. So in other words, these processes exhibit cooperation. As a matter of fact, conditions will not always be as a clear cut as we can see in this table. So it's not only they are completely unaware of each other or directly or indirectly aware of each other. Rather, several processes may exhibit aspects of both cooperation and competition. That means it is productive to examine each of the three items in this list separately and determine their implications for the operating system. Now let's discuss each of those items or those process interaction levels, which will indicate the level of awareness between the processes in details in the following slide. We're gonna start by resource competition. So concurrent processes come into conflict with each other when they are competing for the use of the same resource. In its pure form, we can actually describe the situation as follows. Two or more processes need to access a resource during the course of their execution. That means each process is unaware of the existence of other process or other processes. And each process is to be actually unaffected by the execution of the other processes. It follows from this that each process should leave the state of any resource that it uses unaffected. Examples of resources including input-output devices, memory, processor time, and the clock. There is no exchange of information between the competing processes. However, the execution of one process may affect the behavior of competing processes. In particular, if two processes both wish to access a single resource, then one process will be allocated that resource by the operating system and the other will have to wait. Therefore, the process that is denied access will be slowed down. In an extreme case, the blocked process may never get access to the resource and hence will never terminate successfully. That means in the case of competing processes, three control problems must be faced. First, the need for mutual exclusion, and then deadlock and starvation. For the need for mutual exclusion, let's suppose that two or more processes require access to a single non-shareable resource, for example, like printer. During the course of execution, each process will be sending commands to the I/O device, receiving status information, sending data, and of course, receiving data or sending and receiving data. We will refer to this resource as a critical resource, and the portion of the program that uses this resource would be called the critical section, as we discussed before. So it is important that only one program at a time be allowed in this critical section, in its critical section, and we can't simply rely on the operating system to understand and enforce this restriction, because actually the detailed requirements may not be obvious. So in the case of this printer example, we want any individual process to have control of the printer while it prints an entire file. Otherwise, lines from competing processes will be interleaved. This is an example of mutual exclusion. The enforcement of the mutual exclusion, which is mandatory in concurrency, has actually created two additional problems, as I said before. The deadlock. For the deadlock, let's like talk about the deadlock a little bit. Now, consider two processes, process one and process two, and two resources. So we have two processes and two resources, resource one and resource two. And then suppose that each process needs access to both resources in order to perform part of its function. Then it is possible to have the following situation. Number one, the operating system will assign resource one to process two and resource two to process one. Each process now is waiting for one of the two resources to be released. That means neither will release the resource that is already owned until it has acquired the other resource and performed the function requiring both resources. That means process one and process two are in deadlock. After a final enforcing the mutual exclusion, there are another problem that we might see, which we call it a control problem, is the starvation. So we say processes are starving. What does like starving mean? Suppose that we have three processes like process one, process two, and process three. Each require periodic access to resource R. So we just have three processes and we just have one resource, which is called R. Now consider this situation. If we assume that P1 is in possession of the resource R, while B2, process 2, and P3 are delayed, waiting for that resource. That means when P1 exits the critical section, either B2 or B3 should be allowed to access the resource R. Now assume that the operating system grants access to B3 and that, so if I'm going to assume that the operating system will grant access to process 3 and that P1 again require access before B3 completes its critical section. So now with the assumption that B1 one more time would requires access to the resource R actually before B3 completes its critical section. And if the operating system grants the access to P1 after B3 has finished and subsequently alternating grants access to P1 and B3, that means then P2 may indefinitely be denied access to the resource R, even though there is no deadlock situation, but now P2 is starving because the operating system is alternating access between P1 and B3, and B2 now is starving. That means it's definitely staying without having access to the resource R. This is called starvation. So control of competition involves the operating system because it's the operating system that allocates resources. In addition, the processes themselves will need to be able to express the requirement for mutual execution in some fashion, such as locking a resource prior to its use. And that means any solution will involve some support of the operating system, such as the provision of the lock facility. In this figure, we can see the mutual execution mechanism. In abstract terms, we assume that we have n processes to be executed concurrently. And each process includes critical section that operate on some resource. So critical section in which we operate in some resource, we will call it RA. And it is desired that only one process at a time be in its critical section to enforce mutual exclusion. And in this example, we assume that we have two functions, called the intercritical and the exit-critical. And as a matter of fact, we do have additional code preceding and following the critical section. So these are the two functions that we just referred to it. So these are the two additional code preceding and following the critical section that does not involve access to RA. So in the preceding or even like pre and post the critical section, this code doesn't provide access or involve access to RA because all the processes access the same resource RA. And as I said before, to enforce a mutual exclusion, it is desirable that only one process to be in its critical section. So at this point, the two functions that we allow that we have it prior to the critical section and post to the critical section, which are called intercritical and exit-critical, each function takes an argument, the name of the resource that is the subject of the competition. So you can see here, mutual exclusion through the competition between the two multiple processes. Any process that attempts to enter its critical section while another process is in its critical section for the same resource, will have to wait. It remains to examine specific mechanism for providing the functions intercritical and exit-critical. At this moment, we will defer this issue while we consider the other case of the process interactions. So as you can see in this example, it shows how the mutual exclusion is enforced by using some additional code prior and after the critical section that will only allow one process to enter the critical section at a time to access a shared resource. This is when we deal with processes that are interacting by competition. That means processes are interacting by competing to access a shared resource. So the second level of awareness is a cooperation between the processes. And this kind of cooperation is by sharing resources, which means we are talking about the case of cooperation by sharing um, some resources, and that means those processes that interact with other processes without being explicitly aware of them. For example, we might see multiple processes may have access to shared variable or to shared file or to shared database. Processes may use and update the shared data without reference to other processes, but know that other processes may have access to the same data. That's why we say it's a cooperation by sharing, indirectly cooperation. Thus, the processes must cooperate to ensure that the data they share are properly managed. The control mechanism must ensure the integrity of the shared data. And as a matter of fact, because data are held on resources, devices like devices or even memory, the control problems of mutual exclusion and deadlock and even starvation are again what present. So we were able to see different starvation and deadlock problems, even with indirect cooperation between processes. And the only difference is that data items may be accessed in two different modes, either reading and writing, and only writing operation must be mutually exclusive. So in the first two cases that we have discussed so far, each process has its own isolated environment that doesn't include the other processes. The interaction among the processes are indirect. In both cases, there is a sharing. In the case of competition, they are sharing resources without being aware of the other processes. And in the second case, they are sharing values. And although each process is not explicitly aware of the other processes, it is aware of the need to maintain data integrity. When processes cooperate by communication, however, this is slightly different. That means the various processes participate in a common effort that links all of the processes. So what this means, typically communication can be characterized as consisting of messages of some sort, like there's some sort of messaging between the processes to enforce or to perform communication. And actually, primitives for sending and receiving messages um, may be provided as part of the programming language or even provided by the operating system kernel. So because nothing is shared between processes in the act of passing messages, mutual exclusion is not a control requirement for this sort of cooperation. However, the problems of deadlock and starvation are still present. So if we like in this sort of awareness between the processes, even if they are communicating, they are cooperating by communication, I can show you an example of deadlock as follow. So we could have an example of two processes maybe blocked, each waiting for the communication from each other. So here we are waiting for sort of communication because this is a cooperation by communication. And this is an example of deadlock. If I would like to give you another example of starvation, now let's assume we have three processes, process 1 and process 2 and process 3, actually that exhibit the following behavior. Process 1 is repeatedly attempting to communicate with either process 2 or process 3. And process 2 and process 3 are both attempting to communicate with process 1. A sequence could arise in which process 1 and process 2 exchange information repeatedly, while process 3 is blocked waiting for communication from process 1. So process 3 now is blocked waiting for communication from process 1. So in this example, we can see that there is no deadlock because P1 remains active, but P3 is starving. So this example shows you that starvation could exist. We can see another examples for deadlock when we have two processes that are blocked waiting for communication from each other. So to emphasize on the requirement for mutual exclusion, we know that any facility or capability that is to provide support for mutual exclusion should meet the following requirements. Mutual exclusion must be enforced. Only one process at a time is allowed into its critical section among all the processes that have critical sections for the same resource or shared object. A process that halts in its non-critical section must do so without interfering with other processes. It must not be possible for a process requiring access to a critical section to be delayed indefinitely. So, no deadlock, no starvation. When no processes, when no process is in the critical section, any process that requests entry to its critical section must be permitted to enter without delay. No assumptions are made about relative process speeds or number of processors. Also, a process remains inside its critical section for a finite time only. As a matter of fact, there are a number of ways which the requirements for mutual exclusion can be satisfied. One approach is to leave the responsibility with the processes that wish to execute concurrently. That means processes, whether they are system programs or application programs, would be required to coordinate with one another to enforce mutual exclusion. That means no support from the programming language or even from the operating system. So we can refer to these as software approaches, as we have discussed before. Although this approach is prone to high processing, overheads, and bugs, it is useful to examine such approach to gain a better understanding of the complexity of concurrent processing. So a second approach would actually involve the use of special purpose machine instructions. So now we are talking about the machine level. These have the advantage of reducing overhead, but will be shown to be an unattractive as a general purpose solution because it's on the hardware level. Somehow it's not easy to enforce mutual execution using hardware as compared to the software approaches. And the third approach to enforce the mutual exclusion or to satisfy the fact for a requirement for mutual exclusion is to provide some level of support within the operating system or the programming language. And these are the most common approaches which we will examine in today's lecture as well. Now let's see how we could, so as we talked before about mutual exclusion using software approaches, now let's talk about mutual exclusion using hardware approaches. So in a uniprocessor, concurrent processes cannot have overlapped execution. They can only be interleaved. This is what we know from uniprocessor systems. That means a process will continue to run until it involves an operating system surface or until it is interrupted. Therefore, so if this is the strategy, to guarantee mutual execution, it is sufficient to prevent a process from being interrupted. So this is a way to enforce this by preventing a process from being interrupted to enforce or to guarantee mutual exclusion. This capability can be provided in the form of primitives defined by the operating system kernel for disabling and enabling interrupts. Because the critical section cannot be interrupted, mutual execution is guaranteed. The price for this approach, however, is high. The efficiency of execution could be um, um, degraded because the processor is limited in its ability to interleave between processes. And that means this approach will not work in a multiprocessor architecture, because when the computer includes more than one processor, it's possible and typical for more than one process to be executed at a time. In this case, disabled interrupt, like those interrupts that are disabled, do not guarantee mutual execution. So it's working perfectly for uniprocessor, but disabling interrupts as a strategy of enforcing mutual execution is not working for multiprocessor systems. So let me share with you the abstract view or the pseudocode of disabling interrupts. As long as a process is running, you disable all interrupts and then enter into your critical section. Once you're done, you allow interrupts again, and then you proceed afterwards. This is a primitive way you by disabling or enabling interrupts by the kernel, the operating system kernel, with the hardware support. Another way to do this is by involving some machine instructions, as I said before. So we still try to enforce mutual exclusion, but with the also with the hardware support, but not with the disabling or enabling interrupt strategy, but we will involve some machine instructions. This machine instruction is called compare and swap instruction. Sometimes it's called compare and exchange instructions. So this is machine instruction, wherever you see it. That means we will try hard to enforce mutual exclusion. So this version of the instruction actually it checks a memory location called word. So again, it's a test value. It's called test value. So more or less, a comparison is made between a memory value and a test value. So I'm gonna refer to this as word. I'm gonna refer to this as just the value. And if the memory location current value, so if you're going to compare the memory location current value to the test value, that means it is replaced with the new value. So the test value will be replaced by the new value. So there's a swap operation that will take place. Otherwise, it is left unchanged. And the old memory value is always returned. Thus, the memory location has been updated if the return value is the same as the test value. This machine instruction is atomic instruction. Therefore, it has two parts. The first one, a comparison, and the second one is a swap operation. A comparison is made between a memory value and a test value. And then the swap operation takes place if the two values are the same. The entire compare and swap instruction is carried out automatically. That means it is not subject to interruption. Because it's not subject to interruption, this way, it could be easily used to enforce mutual exclusion. So another version of this instruction might return a Boolean value, true if the swap occurs, false otherwise. We can see some version of this instruction is available on early processor families like A886, IBM Z series, and so on. And most operating systems use this instruction for support of concurrency. So if we look to the following graph, how the following code, how we could actually support mutual exclusion, how we could enforce mutual exclusion using hardware support, we can see in this figure a mutual exclusion protocol based on the use of the swap, the compare and swap instruction. A shared value variable is called bold, which is initially initialized to 0. The only process that may enter its critical section is the one that finds bold equal to 0. all other processes attempting to enter the critical section, they will go into a busy waiting mode. That's why we refer to the term busy waiting or spin waiting, which refers to a technique in which a process can do nothing until it gets permission to enter its critical section, but continues to execute an instruction or set of instructions that test the appropriate value to gain entrance. When a process leaves its critical section, it resets the pulse back to 0. At this point, one and only one of the waiting processes is granted access to its critical section. The choice of which process would depend on which process happens to execute the compare and swap instruction next. So in the graph on the right-hand side, we can see a mutual execution protocol based on the use of an exchange instruction. Also, the shared bolt value is initialized to 0. Each process will use a local variable key that is initialized to 1. The only process that may enter its critical section is the one that finds bolt equal to 0, and then it executes all other processes, it excludes all other processes from the critical section by setting bolts to 1. When the process leaves its critical section, it resets bolts to 0, allowing another processes to gain access to its critical section. As you can see here, it's all about manipulating your code to enforce that only one process will have access to its critical section and no other processes will be in their critical sections to access the shared resource unless this process is executed. This could be done either by the software approach which we shared before, or even by enforcing enabling or disabling interrupts, or even here by using the swap, the compare and swap function or the exchange function. So either we are using the compare and swap function, the swap function, or we are using the exchange function. It doesn't allow any process to go into its critical section unless all other processes are not in their critical sections. This way will actually enforce mutual execution, and it may have some starvation, but it is really working for enforcing mutual execution. Why we use these special machine instructions, either the compare and swap or the exchange functions, has number of advantages, because it is applicable to any number of processes on either a single processor or multiple processors sharing main memory. Like if you compare it to the enabling or disabling interrupts, and enabling or disabling interrupts were successful on a uni processor, it was not successful on multiprocessor. However, the special machine instructions, it's successful, that it's working because it's working on either single processor or multiprocessor. It is simple and it's easy to verify. It can be used to support multiple critical sections. Each critical section can be defined by its own variables. So we can use multiple variables. Each variable will allow access to different critical sections. So although there are some advantages of using the special machine instruction to enforce mutual execution, however, it comes with some disadvantages. The busy waiting is employed. So we still have busy waiting protocol. Thus, while a process is waiting for access to its critical section, it continues to consume the processor time. This is one of the major disadvantages. Also, starvation is possible. When a process leaves a critical section and more than one process is waiting, the selection of a waiting process is arbitrary. Thus, some process could actually indefinitely be denied access to any resource. So that's why starvation might happen, and this is not good as well. Deadlock is possible. So we might not, like for the machine instructions, we see minor cases of deadlocks, but it is possible to happen. Like consider the following scenario on a single processor. If I'm going to give you a single scenario where process 1 executes the special instruction of compare and swap and then exchange or exchange, and then enters its critical section. Then if we assume that process 1 is interrupted, that means the processor, so I assume it's interrupted. So the processor now will be given to process 2, which we assume that it has high priority. So if P2 now attempts to use the same resource as P1, so if you assume that P2 will attempts to use same resource as P1, it will be denied access because of the mutual execution mechanism. At this point, it will go into a busy waiting loop. However, P1 will never be dispatched because it is of low priority than the ready process P2. So that will lead to a deadlock. Because of these drawbacks of the software approaches that we have seen so far, and also the hardware solutions, either by enabling or disabling interrupts or using special machine instructions, now we need to look to different mechanisms that involves the programming language and the operating system. So now we turn to the operating system and programming language mechanisms that are used to provide concurrency. In this table, we summarize different mechanisms that are in common use. And in today's lecture, we will start by semaphores, and then monitor, followed by monitors, and messages. Semaphores, like from the definition in this table, it's just an integer value that is used for signaling among processes. With semaphores, we have only 3 operations that might be performed on a semaphore. It's just an integer value, and we allow only 2 operations on the semaphore, all of which of those 3 processes are atomic. That means once they start, no way to interrupt it. Those processes, those functions, or those operations are initialize, decrement, and decrement the semaphore. The decrement operation may result in blocking of a process, and the increment operation may result in unblocking of a process. Semaphores are also known as counting semaphores. Sometimes we call it general semaphores. We have 2 special types of semaphores. The first one is called the binary semaphore, and the second one is called the mutex semaphore. So binary semaphore is a general semaphore. However, it only takes value between 0 and 1. Mutex semaphore, it is similar to binary semaphores. The key difference between the binary semaphore and the mutex is that the process that locks the mutex, which means sets the value to 0, must be the one to unlock it, which means it will set the value back to 1. And then we already talked about condition variables before. We talked about the race conditions before, but when it comes to monitors, we will talk about condition variables. What is a condition variable? Is a data type that is used to block a process or even a thread until a particular condition is true. Condition variables will be widely used in monitors, and monitors is a simple construct that encapsulate variables, give access to procedures, and also initialization to the code within an abstract data type. This monitor variable may be only accessed via its access procedures, and only one process may be actively accessing the monitor at any time. The access procedures are critical sections. A monitor may have a queue of processes that are waiting to access the monitor. We will also talk more about mailboxes and messages, which means for 2 processes to exchange information, and that may be used for synchronization. This is where we say messages communication. And then we will also talk about spin lock, in which mutual execution mechanism in which a process execute in an infinite loop waiting for the value of the lock variable to indicate availability. Now let's discuss each one of those mechanisms in more detail, starting by semaphore. The first major advances in dealing with the problems of concurrent processes, actually it started in 1965 when Dijkstra has developed his algorithm. And Dijkstra was concerned with the design of an operating system as a collection of cooperating sequential processes. And with the development of efficient and reliable mechanism for supporting cooperation, these mechanisms can just as readily be used by user processes if the processor and the operating system make the mechanisms available. The fundamental principle in this is as follows. Two or more processes can cooperate by means of simple signals, such that a process can be forced to stop at a specific place until it has received a specific signal. Any complex coordination requirement can be satisfied by the appropriate structure of signals. For signals, special variables called semaphores are used. To transmit a signal via semaphores, I'm going to call it S for now. So generally, we're going to use the variable S, stands for semaphores. A process will execute two primitives. The first primitive is the sem signal, and the second primitive is a sem signal, and the second primitive is a sem wait. To receive a signal via semaphore S, a process executes the primitive. So to execute to receive a signal via the semaphore S, a process will execute the primitive sem wait. And to transmit a signal, the process will execute the same signal. So the same signal is for a process to transmit a signal. And same wait means a process is receiving a signal. So when a process receives a signal, it will initiate a same wait. And when a process actually transmitting a signal, the primitive same signal will be initiated. If the corresponding signal has not been yet transmitted, the process is suspended until the all transmission takes place. To achieve this strategy, and actually to achieve the desired effect as well, we can look to the semaphores as just a variable. And this variable has integer value upon which only three operations are defined, including the same wait and same signal. We add the initialization function. A semaphore may be initialized to a non-negative integer value. And then we do have the two primitives which we discussed before, including the same wait operation and the same signal. Same signal means that a process is transmitting a signal. Same wait means a process is receiving a signal. When a process is receiving a signal, it decrements the semaphore value. When a process transmitting a signal, it actually increments the semaphore value. So when the process decremented the semaphore value using the same wait operation, if the value becomes negative, then the process executing the same wait is blocked. Otherwise, the process will continue execution. For the same signal operation, it increments the semaphore value. And if the resulting value less than or equal to 0, then a process is blocked by the same wait operation, if any, is unblocked. Otherwise, there is no way to actually inspect or manipulate semaphores except with the use of these three operations. So I would like to explain for you these operations as follow. So we do have initializations, we do have a same way to decrement the variable, we do have a same signal to increment the variable. To begin, the semaphore always has a value 0. And then actually. The semaphore always has a value 0, and then or even positive value. If the value is positive, that value equals the number of processes that can actually issue a wait and immediately continue to execute. If the value is 0, on the other hand, either by initialization or because a number of processes equal to the initialization semaphore value have issued a wait signal, a semaphore wait procedure, that means the next process to issue a wait is blocked and the semaphore value goes negative. Each subsequent wait would drive the semaphore value further into minus territory, and the negative value equals the number of processes waiting to be unblocked. Each signal unblocks one of the waiting processes when the semaphore value is negative. So more or less, this is how the three operations are working together to enforce mutual execution using semaphores. First, you initialize the semaphores by either 0 or some positive value, and check on the value if it's positive, which we understand that this value equal to the number of processes that can issue a signal, a wait operation, and then immediately continue to execute. And then if the value is 0 at this point, the semaphore value, the process will initiate a wait operation, and then the semaphore value would go negative, and then we know that the negative value of the semaphores will determine those processes that are blocked in waiting for the semaphore signal to be received again. So consequences of using such a strategy, which enforcing mutual exclusion, will, like, I have summarized it for you into three consequences. Like, they look interesting. In general, there is no way to know beforehand if a process decrements a semaphore, whether it will be blocked or not. After a process increments a semaphore and another process gets woken up, both processes continuing running concurrently. There is no way to know which process, if either, will continue immediately on a uni-processor system. When you signal a semaphore, you don't necessarily know whether another process is waiting, so the number of unlocked processes may be 0 or 1. These are the main consequences of the semaphore definition. If we look to the following pseudocode, which suggests a more formal definition of the primitives for semaphores, at this, which we explained it before, the same wait operation and the same signal operation are assumed to be atomic operations. Means once a process initiates either or, no other process can interrupt it. As we said before, in the same wait, we start by decrementing the semaphore count. So initially, we define a semaphore by as an integer number, and of course, we do have queue in which we would have the blocked processes lining up in this queue. And then based on the initialization of the semaphore, if a process initiates a same wait, it starts by decrementing the variable. If the variable is negative, this process would go into the queue and this process is blocked. While in the same signal, we will increment the semaphore value. And if it's negative or equal to 0, that means we have to remove it from the queue and then place the process into the ready list for execution next. So this is for the general semaphores, or sometimes we call it the count semaphores. As a matter of fact, a more restricted version of the semaphores is known as the binary semaphores. A binary semaphore may only take the value of 0 and 1 and can be defined by the following three operations. A binary semaphore may be initialized to 0 and 1, which is part of the initialization. The same wait, so we do have sem signal B, so B stands for binary, and same wait B stands for waiting, but for a binary semaphore. The same wait operation So we still have the binary semaphore and it has only 0, 1 value. We still have the queue for lining up when the process is in wait situation, blocked until it is released for execution. For the same wait operation, it first checks on the semaphore value. If the value is equal to 0, then the process executing the same wait is blocked. If the value is equals to 1, then the value is changed to 0 and the process continue execution. On the other hand, for the sim signal operation, it checks to see if any process are blocked on this semaphore. That means semaphore value equal to 0. If so, then a process blocked by the same wait operation is unblocked. If no processes are blocked, then the value of the semaphore is set to 1. In principle, it should be easier to implement the binary semaphore, and it can be shown that it has the same expressive power as the general semaphore. But in most operating systems, they use the general semaphores, especially if you have multiple processes. To contrast the two types of semaphores, the non-binary semaphore is often referred to as a counting semaphore or general semaphores, and as a matter of fact, it is widely used as compared to the binary semaphore. So a concept related to the binary semaphores is the mutual exclusion look. So the mutex. So the mutex, which we refer to as the mutual exclusion lock. A mutex is a programming flag used to grab and release an object. When data are acquired that cannot be shared or even processing is started, that can be performed simultaneously elsewhere in the system. At this point, the mutex is set to lock, typically a value at 0, which blocks other attempts to use it. The mutex is set to unlock when the data are no longer needed or the routine is finished. A key difference between the mutex and a binary semaphore is that the process that locks the mutex, which means it sets the value to 0, must be the one that unlocks it, which means it has to set the value to 1. In contrast, it is possible for one process to lock a binary semaphore and for another to unlock it. So for semaphores, for both either counting semaphores and even binary semaphores, a queue is used to hold the processes waiting on the semaphore. The question arises here based on the order in which processes are removed from such a queue. Actually, the first removal policy is the first in, first out. The process that has been blocked the longest is released from the queue first. So this is the first in, first out strategy. A semaphore that comes with the definition that includes this first in, first out strategy is a strong semaphore. However, a semaphore that doesn't specify the order in which processes are removed from the queue is called a weak semaphore. So let's now take this example of the operation of strong semaphores and see how actually this could be achieved. And we can see the sequence of removal and addition based on the value of incrementing or decrementing the semaphores by employing the sim wait and the sim signal procedures. Let's take the following transition diagrams showing entering and removing, adding, removing processes into the queue based on the semaphore value. Let's look to the initial situations in number 1. So it goes in sequence. I'm going to show you how this goes in sequence. So what actually happened is A is running. So A is running by the processor. And B and C and D are ready. So we know that in the ready queue, we have B and a C and a D in the order of arrivals. And the semaphore count has a value 1. So I'm going to use the variable s to indicate the semaphore variable, and it is initialized by a value 1. Indicating indicating that one of the D's result is available. Because in this program, actually, processes A and B and C depends on the result from process D. So the assumption here, so I'm gonna just write it down. The assumption in this example is that processes A and B and C, they would depend on the results from process D. So when we have a semaphore count equals to 1 initially, that indicates that one of the D's results is available. Now let's see what will happen when A issue a same weight instruction. So when A would issue a same weight instruction on a semaphore S, the semaphore will be decremented to value 0, and A can continue to execute. Subsequently, it rejoin the ready queue again. Then B will be running by the processor, eventually will issue a same weight instruction, and it is blocked, which will allow D to run again. When D completes a new result, it issue a same signal instruction, which allow B to move to the ready queue. Keep in mind that when B has initiated when A has initiated a same weight, the value of the semaphore has been decremented by 1, so from 1 goes to 0, and then when B initiate another same weight going to the block state, so the value has been decremented again to a -1. Now, when D is completed, so it initiate a same signal, so it incremented the value of the S again, so it goes back to 0. And that means D will rejoin again the ready queue, and C will begin to run. But it is blocked when it issue a same weight instruction. So we can see it might go to the same weight instruction again. So if we actually like go over multiple iterations, we can see that A and B run and are blocked on the semaphores, will allow D to resume execution. When D has a result, it will issue a same signal, which transfers C to the ready queue. Later, if we look to later cycles of D, will release A and B from the blocked state. So we can see here multiple iterations of incrementing and decrementing the semaphores. And once a semaphore is, once a process initiates the same weight, it will decrement the semaphore. One, it decremented semaphore, we have to check on the value of the semaphore to follow a certain procedure of blocking other processes. And once it is ready for execution, that means the process will initiate a same signal. So we're gonna increment the value of the semaphores for the process to be added to the ready queue. So this is an example of the operation of strong semaphores. And as a matter of fact, for the mutual exclusion algorithm, that will be discussed based on the use of strong semaphores. We assume that it guarantee freedom from starvation, while the weak semaphores do not. So if you are using strong semaphores, the strong semaphores, they guarantee freedom of starvations, while weak semaphores, they don't. From now on, we will assume semaphores because they are strong, because they are more convenient, and because this is the form of semaphore typically provided by the operating system. In this figure, you can see a straightforward solution to mutual exclusion using semaphores. If we assume we do have n processes identified by the array from process 1 up to process n, all of which need access to the same resource. Each process has a critical section. And used to access the resource. In each process, we do have the same weight, and each process can initiate the same weight or can initiate a same signal. It always initiate same weight before the critical section, and it always initiate a same signal after the critical section. The same weight is executed just before the critical section, because if the value of the semaphore becomes negative, the process is blocked. And if the value of the semaphore is 1, then it is determined it is decremented to 0, and the process immediately enter into the critical section. And because the semaphore is no longer positive, no other process would be able to enter its critical section. The semaphore is initialized to 1 in most of the cases. Thus, the first process that execute a same wait will be able to enter the critical section immediately, setting the value of the semaphore to 0 after initiating a same wait. Any other process attempting to enter the critical section will find it is busy and will be blocked, setting the value of the semaphore to -1. Any number of processes may attempt entry. Each such unsuccessful attempts result in a further decrement of the value of S. When the process that initially entered in its critical section departed, that means S is incremented and one of the blocked processes, if any, is removed from the queue of blocked processes. This is by initiating a SEM signal. When it's next, for this process, when it's next to be scheduled by the operating system, now it has the right to go or to enter its critical section because no other process now is in the critical section. So if we look to the following figure, we can see a possible sequence for 3 processes using the mutual execution principle using semaphores, in which we do have a queue for the semaphore, which we call it lock. We initiate the value. We are monitoring the value of the semaphore lock, and starting by value 1. We can see we have 3 processes, A and a B and a C. A bolded arrow means the process is in the critical section, and a thin arrow means the process is in normal execution. A dotted arrow means, or like a dotted line means it is blocked on the semaphore lock. Note that the normal execution can proceed in parallel, but that critical regions are serialized. So in this example, 3 processes will access a shared resource protected by the semaphore lock. Process A execute a same wait. On the lock, because the semaphore has a value of 1 initially, at the time of the same wait operation, that means A can immediately enter its critical section. So we can see a bolded arrow, that means A in the critical section. And the semaphore takes the value of 0. While A is in the critical section, both B and C would actually perform a same wait operations on and are blocked pending the availability of the semaphore. When A exits its critical section, so it will initiate a SEM signal. So each process, when it initiates a same wait, it decrements the value of the semaphore. First, this was done by B, and now it joined the block queue. This was done by C, it joined the block queue again. So now the semaphore was decremented to a value -1, followed by the value of -2. And then when A ends its execution, it incremented the semaphore value again. So the value goes back to -1. And now we will see that B should be in its critical section. And means when it's critical section 1, it is released because we know that C is still in the queue. It will initiate a SIM signal, which means we're going to increment the semaphore by 0, and C can actually be in its critical section at this point, which would increment once it's completed by a SIM signal, the value to 1, allowing any other process to enter a critical section once C is completed. So we can see that strong semaphores are really efficient in the fact that it is first come, first serve, and in the fact that it can be widely used to enforce mutual execution to guarantee deadlock-free and starvation-free.